In our last video, we defined the cross product and did an example of how to actually calculate the cross product. You definitely need to get used to calculating cross products. But in this video, I'd like to talk more about properties of the cross product. What's interesting about them, why we use them. Well, first off, remember the whole reason we take cross products in R3 is to find a vector that's orthogonal or perpendicular to your first two vectors. That's the whole reason you take a cross product. So here are some properties of the cross product. Let's start with property 1. Property 1 is basically going to be a restatement of this sentence. If I do the dot product of u with u cross v, then I get 0. That's because the way to decide if your vectors are orthogonal is to take a dot product. If your dot product is 0, then your vectors are orthogonal or at a 90-degree angle. You could similarly write down v dot u cross v is also 0. So that's property 1. Property 2 is this. The direction of your vector u cross v is determined by the so-called right-hand rule. So let's talk about what that means. First, maybe I should do an example to illustrate what I'm going to say. So let's take the cross product 1, 0, 0. That's actually I hat. And let's cross it with j hat. So let's do 0, 1, 0. So the way that we calculate cross products was to form this 3 by 3 array. In the top row, I have I hat, which is actually this vector, j hat, which is the second vector, and also k hat. In the middle row, I write down 1, 0, 0, my first vector, and in the last row, I write 0, 1, 0. So to take the cross product, I imagine crossing off the row and the column containing I hat, and I'm left with 0, 0, 1, 0. If you take that 2 by 2 determinant, you get 0 minus 0. So I actually get 0 I hat. The second term in the cross product has a negative sign in it. So there's a negative sign in the second term. The second term, I imagine crossing off the row and column containing j, and I still get 0. So the second entry, 0j. And then the last calculation will be crossing off the row and the column containing k hat. So I cross off that row and that column. I take the remaining 2 by 2 determinant. I get 1 minus 0. So I get 1 times k hat. That gives me k hat, which is the vector 0, 0, 1. So if I were going to draw a picture of what's going on here, I can draw my three-dimensional axis system. So here's x, y, and z. X is drawn in perspective, but x is really the axis that's coming straight up out of the page. Y is the axis going to the right, and z up. So the vector I hat is the vector 1, 0, 0. So this vector here is I hat. And I'm taking the cross product of that with j hat. I got a vector in the positive z direction. I got k hat. But when you take the cross product, the only thing that you're guaranteed is a vector that's orthogonal to your first two at a 90-degree angle with your first two. That means I could be going straight up in the z direction, or I could be going straight down. Both directions are at a 90-degree angle with my two original vectors. Which direction does the cross product give you? That is given by what I'm about to describe. It's the right-hand rule. So here's how you do the right-hand rule. You have to take your right hand, obviously. You point your index finger in the direction of your first vector. Then you point your middle finger in the direction of your second vector. Then your thumb will be in the direction of the cross product. So again, index finger in the direction of your first vector, middle finger in the direction of your second vector, thumb will be the direction of the cross product. So let's try that with this picture. So I'm going to put my index finger in the direction of X, which is coming straight out of the page. And then I'm going to put my middle finger in the direction of the Y-axis. My thumb, so I'm trying to do that. My index finger is going straight up. My middle finger is going in the direction of Y. Then my thumb is indeed pointing in the direction of Z. So that's the so-called right-hand rule. That's property 2. Okay, let's look at property 3. Property 3 says if I do U cross V, I get negative V cross U. So if I reverse the order of the multiplication, I get an extra negative sign. When you have a negative sign in front of a vector, that means you're reversing the direction of the vector and you're going in the opposite direction. Property 3 follows from the right-hand rule. Let's suppose I did this calculation again. Let's suppose I did the same cross product but in the reverse order. If I did this product in the reverse order, let's see how the right-hand rule would change. So next I'm gonna do my index finger in the direction of J. So I'm gonna do my index finger in the direction of J. I'm gonna do my middle finger in the direction straight up. So here, now I have my index finger pointing in the direction of Y. I have my middle finger trying to point straight up in the X direction, and my thumb is now pointing down, the opposite direction I started with. So that's a description of why you get an extra negative sign when you reverse the terms U and V. Okay, here's another property, property 4. If you do the cross product of U with itself, let's just do this really quick. So I get I hat, J hat, K hat. Let's say U is ABC, that's my vector maybe, and I'll write it twice because I'm taking U cross U. If you do the calculation, I cross off the row and the column containing I hat, and I have the 2 by 2 determinant BC, BC. Now that will be B times C minus B times C. That would give me 0 I hat. The middle term has an extra negative sign in the cross product. I cross off the row and the column containing J hat, and I get AC, AC. Taking that 2 by 2 determinant, I get A times C minus A times C. So I get 0 J hat. And similarly, I get 0 K hat. This is the 0 vector. 0, 0, 0, not the 0 number. I get a vector, the 0 vector out. Sometimes we use the notation 0 with a bar over it to denote the 0 vector. That was not the 0 number. It's a vector. So if you take a cross product of a vector with itself, you get the 0 vector. And in fact, as an extension of property 4, two vectors are orthogonal. No, excuse me, I don't want orthogonal. Two vectors are parallel. I want two vectors to be parallel if and only if you take their cross product, U cross V, and you get the 0 vector. You get the 0 vector. If U is taken with U, the cross product of U with itself, then you get the 0 vector. But in general, if you scale U, if you have a multiple of U, then you're parallel to U, and still you get the cross product equaling 0. It kind of makes sense that the cross product would give you maybe some strange answer when you start taking two vectors that are parallel, because if you think about the geometry, if two vectors are parallel, like my finger and my pencil, there's not a single direction that's perpendicular to both your parallel vectors. because any vector, there's vectors in a 360-degree rotation that are going to be parallel to both, perpendicular to both of your parallel vectors. So anyway, that's property 5. And the last property I want to write down is property 6. So property 2 gives me the direction of the cross product vector. But as we know, vectors are described by two things: a direction and a length. So property 2 gives you the direction. I'm going to show you the length now. What is the length of U cross V? Well, you could do a bunch of algebra. It's kind of messy, but if you did a bunch of algebra just by expanding the cross product, writing U as A, B, C, write V as X, Y, Z, do all the calculations, it'll turn out that you could simplify things and get the magnitude of the cross product is the magnitude of U squared times the magnitude of V squared minus the dot product of U and V squared. Now, based on our understanding of the dot product, this is the magnitude of U squared, the magnitude or the length of V squared, and then I could do the length of U, the length of V, times cosine the angle between the vectors. So we know that that's the main reason people take the dot product, is because it tells you information about the angle between the two vectors. Now you could factor out a magnitude of U squared, a magnitude of U from the square root. The magnitude of V, you could factor it out of the square root. And what you're left with, not squared, and what you're left with is the square root of 1 minus cosine theta squared. Using the well-known trig identity, this is equal to sine squared. So the final amazing conclusion to property 6 is that this is the length of U times the length of V times sine the angle between them. Very similar to the cross product, dot product. The dot product said the dot product is equal to the length of U times the length of V times cosine the angle between them. Here, I have the magnitude, the length of the vector found by the cross product is very similar. All right, wonderful.